So with regard to the assignments, I was thinking that I will give you an assignment next class. So on Thursday, I will put it up on WeLearn. So how long do you normally get for an assignment? Like few days or more? Someone answer, maybe Dhavala answer.
Ma'am, roughly a week or more, like 8 to 10 days.
You get 8 to 10 days. Oh, fine. And what about a small test on next week Tuesday?
Ma'am, that also we took minimum 6 hours we had last time. That also for an NSEM test we had. So
No, this will be just a short one. I will. Uh, is it like on a during class hours or is it outside class hours?
outside class hours is more preferable, ma'am, because someone might have a class after chemistry. So
Okay, okay. So then I will. So how can I get your schedule? Can one of you send me your schedule? Like, just how will I know when to schedule it?
ma'am, the general timetable is on the website.
Yeah, but how? But like y'all are from different courses, right? Not all of
Huh.
you have the same course. How?
Ma'am, we'll conduct we'll ask the opinions, then like we'll give you the like entire outlay of the batch, then like when to conduct and what mode.
Okay, okay. Then find me a slot of like approximately 2 hours.
Okay.
It will be a short test next week sometime.
Okay, ma'am.
Okay. Okay. So now, no, there's still 3 minutes. We will wait for the others to join. Anyone else with any more doubts in this
Ma'am,
point?
I have to I want to convey something.
Yeah, sure, sure.
Ma'am, regarding the discussion forum, you
Yeah.
told that whatever doubts we have, we should post it on the discussion forum. But I have found that on the discussion forum, the new thread will be uploaded by the instructor only, not the students. If we can reply the thread, means if you write one like any queries, if you post a thread, then I can, or any student can type a reply.
Oh,
I have a doubt like that. We can't
oh.
post it as a thread. That's
Uh,
what I want to say.
okay, I was not aware of that because of course I can't
I
open it.
found it in other subject. I found it. That's why I want to convey it to you.
Okay, so then what would you like me to do? Okay, I will just open threads for every lecture then, and you can put your doubts in that lecture. So I will just say lecture 1, lecture 2, lecture 3, like this. Okay.
Yeah. Yeah.
Yeah. Okay.
Okay. Thank you, ma'am.
Ma'am, I had one more small query.
Yeah, sure.
In the hand notes, like the for the verification of the Stefan Boltzmann law, like
Hmm.
when intensity is sigma t power 4,
Yeah.
and we proved by going through intensity's spectral density into c by 4.
Hmm.
So we arrived at the conclusion that average velocity in any one direction is a net average by 4.
Yes. Yes.
So I couldn't understand like how does this prove the intensity and the spectral energy density relation?
Okay. So let me see exactly what it is. Hmm. So this is from the PDF, right, where they have derived the Stefan Boltzmann law. Can you tell me exactly where that is? So your question is that the average velocity is of c by 4. But
Yes,
you
ma'am. It is I think in part 7, like towards the end of the hand notes.
yeah. Okay, so this 4 by C term, it comes from when we go from this spectral energy density in terms of U to B. So if you look at the PDF, they have explained it there. This C by 4, it is so what we derived in the hand notes is spectral energy density. And then there is something called specific intensity of black body radiation. And when you convert between this U and the specific intensity B, you get this factor of C by 4. So it is just to so you add, when we start with this 4 by C in the before we estimate sigma, in order to match the two notations, because the Stefan-Boltzmann law, when it was proposed, the energy quantity that it dealt with was the specific intensity and not the spectral energy density. And to convert between them, you need this factor. So if you look at the notes, you can see how to go from U to B.
No, ma'am, that I understood. After
Oh,
that, there is the verification part, right? I is equals to U into C by 4, where we use the Maxwell's equation.
yeah.
So there we got Ci is Ca by 4. So how it is actually related to the intensity and spectral density?
I don't understand exactly. I mean, how it is related.
As in, why did we prove that like Ci is Ca by 4?
Oh,
And
why?
we got the conclusion that I is equals to U into C by 4.
Okay, why we didn't prove it? Okay. Uh, Actually, even I have not worked it out. I just accepted that it would be like this because it is related to the definitions of how you define spectral energy density and how you define specific intensity. So these are very subjective terms. And if you see, I myself am not sure exactly how they are related directly. If you are really interested, I will look into this a little bit more. I don't know myself.
Okay, ma'am. Thank you.
Okay, so now it's 4 o'clock, so I will start presenting. I hope all the people who want to come have been able to come.
Hello, ma'am. Am I audible?
Yes, please.
Ma'am, actually, the PDF which you gave on black body radiation,
Yes.
there was something, the spectral energy density is 8 by kT V square by C cube. That is in derived equation. After that, you have given that something part was not required like that. Here, I have got the brightness was mentioned. I couldn't understand the relation between the brightness intensity and the spectral energy density, which was mentioned in that PDF.
Okay. So I have actually put that not required because these definitions are very subjective. So I tried to look into the exact definitions for these quantities, and it seems that people don't really agree on this. Some people call the brightness as spectral energy intensity as well. So because it is confusing, you don't need to go into it.
But I think in the handwritten notes, you have asked us to derive the Wien's displacement law by means of that frequency. So if we are trying to derive it by frequency, then we shall take the help of that definition only.
No, that is not necessary. You can do it without it as well.
Because in the PDF, because ma'am, okay, I shall try it then.
You can try it just by replacing the wavelength with frequency. You do not need to change the quantity that you are computing. It is fine.
Okay, ma'am.
Excuse me, ma'am. Can you hear me?
Yeah, I can hear you.
While in the handwritten notes, while calculating the number of nodes, you have taken A to be nx lambda x by 2. It can be anything, nx lambda x by 3. It is actually the wavelength in which we are distributing A. The wave we are distributing in that A length. It is actually, na?
No, we want the nodes to be at the walls. So we don't want the crest or the trough to be on the wall. We want the amplitude to be 0 at the wall. So that is why only those waves which have wavelengths which are half or integral multiples of half the box length are allowed. Yeah.
But if we take,
we don't want the waves to fit. We want them to have nodes at the wall.
no, just our main purpose is that we want nodes except then the walls, na? Between the boundary, that is.
Yeah. We want at the boundary it should be 0 amplitude. The wave.
Then it can be also lambda by 3. We get two modes of two crust and trough na, between the boundary. If it is lambda by 3 as well.
Lambda by, it will be 3 lambda by 2 if you want two like one crest and two troughs.
Okay.
Yeah, it's 3 lambda by 2, not lambda by 3. Isn't it?
Ma'am?
The length of the box. If like you are saying, like two nodes in the middle and two nodes at the end, then it is the length of the box is 3 times lambda by 2.
Hello, ma'am.
Yeah.
At the specific temperature, does the maximum frequency and the maximum wavelength will occur simultaneously?
No, it is opposite. Maximum wavelength means minimum frequency.
Okay, actually Wien's displacement law, we have already derived that lambda max is equal to something 0.29 by T, means lambda is inversely proportional to temperature.
Yes.
But ma'am, when we replace that lambda by means of frequency, then we get the frequency comes down, so frequency gets directly proportional to temperature, like that.
Yeah, that is correct. Yeah.
But ma'am, the relation for frequency is actually frequency equal to 59 by temperature, like that, as I have read in the PDF.
Yeah, so actually there is a problem there. So that is why I suggested that as an exercise. So deriving Wien's law with wavelength and deriving it with frequency, it does not give the same result.
But ma'am, there also a statement was mentioned that this frequency is actually not like that. The relation which we use would be equal to f lambda, like that. So what is the significance of this?
Yeah, so the significance here is that the derivation that we do for Wien's law from Planck's law, that is not perfectly accurate. So this is sort of a approximate derivation in a way. That is why the frequency and the wavelength, they do not match. In reality, of course, you should be able to get the same peak. It should not differ, but it does differ if you work it out like we have done. So that was the point of the exercise. You will see that it does not match.
Will the results vary? Will the results be something variation or like discrete? Which will we get some contradiction like that?
You will get You mean you will get a contradiction in the expression. So this
because ma'am, from Wien's displacement law, lambda max is 0.29 by t I am getting.
yes.
And in terms of frequency, when I going to derive, I am getting something 59 gigahertz by t. Like that I am getting, because I am plotting the two answers. But I am unable to apply that.
Just using this C, like lambda nu equal to C, you cannot. So they are not directly related. So just using lambda nu by C, you cannot convert the two laws. You
Yeah,
get different.
that was mentioned.
Yeah.
So why this discrepancy is coming? That's the point.
Yeah, this discrepancy is coming because the law, the Planck's law that we started from, that is also not an exact law. It still involves some approximations when you derive it. So that is why deriving, when you look at the lambda version and you look at the new version, the Planck's law curves still obey this C is equal to lambda nu relation. But when you obtain a derivative law from it, it becomes wrong. So the Wien's displacement law turns out to be different unless you have a even better Planck's law. So this is possible.
And in one question you have asked us to just comment on the results which we obtained from the both. So is in the comment, are you expecting us that the point that we are not getting the C out of it from the lambda max and P max?
Yeah. I just expect you to note that this is possible and maybe suggest that the starting point is wrong.
Okay, thank you.
That is all. That is all. I don't want you to have a solution to it exactly. Just write what you think. Actually, I did not even expect you to do this assignment. But okay, but it's nice that you have attempted it.
Excuse me, ma'am.
Yeah.
Ma'am, in the part on the derivation where we were kind of like taking components of the wavelength in the 3 dimensions, I couldn't understand. I was thinking that we should have a lambda x is equal to lambda cos alpha for the x direction and something like that. Why do we have lambda is equal to lambda x cos alpha?
Because we want to consider a general wave. Like the waves don't necessarily travel parallel to the sides of the box. It can just travel in any direction. So we wanted to do general wave.
No, it was written that we are taking the component in the wave normal direction. Actually, didn't understand that, because if we are generally looking at components, it should simply have been that the x component of the wave lambda x should be lambda cos alpha. But I think we are taking some different angle for that. That's why we are getting lambda x equal to lambda cos alpha. So can you explain that part? I didn't get how we were taking the component of which part of the wavelength is on that for the x direction and y direction.
Oh, that is just because the angles are defined with respect to the wave normals. If you so let me just open the figure since I have it already. So if you look at the figure, so lambda is the direction in which the wave is traveling. Okay, then you have so the gap between these planes is lambda. Then we have the angle with the x-axis as alpha, and okay, so you would have just said lambda cos alpha is the component in the x direction, but we don't want the component in the x direction. What we want is a condition on what the x component should be. So our question is different. So we want the distance between the wave fronts at the x-axis.
Oh, okay.
Yeah, so our question is a bit different. You see. So our question, the original question was, what lambdas are allowed to have standing waves in this box? So we don't want to take a lambda and see how it travels. We want to find out what lambdas are allowed. Okay. Yeah. Fine. So I will continue then. Okay. So last class we started with the failures of classical mechanics, and the first thing we did was black body radiation. And as I can see, most of you have gone through this. So we found that the classical law, the Rayleigh law, could not explain the curve, and the quantization of the energy of oscillators in the black body, which emitted radiation, this helps us explain the observed radiation curve.
Ma'am, I have a question regarding this one. How did the quantization of energy levels actually intuitively help solve the ultraviolet catastrophe? Because according to classical mechanics, if we had a continuous spectrum of energy, then the energy could be increasing till an infinite level. So what difference did it make if I assume that only discrete energy levels are allowed? Because even then that I could say that the energy could be increasing in discrete levels.
Yeah. Sure. I guess you also put up a question on Wheeler. I answered it a few minutes back.
Oh, I didn't see that.
No problem. I can repeat it for everyone also. The thing is that the fact that we quantize the energy, it helped us come to this, to the fact that the average energy per mode of oscillation which radiated frequencies nu, or around the frequency nu, this and average energy turned out to depend on the frequency that we were considering. So the higher the frequency, the lower was the energy emitted at that frequency. So it was the conclusion from quantizing the energy. So if you see the average energy from the structural picture, it was constant. So it did not matter what frequency I was considering. The energy was still K for every frequency. But when we quantized it and did the summation instead of integral, we obtained an expression where you had the frequencies. So it depended. So the average energy that was emitted at that frequency depended on the frequency. And this was such that it avoided the ultraviolet.
Okay, ma'am, I got it. Okay.
Ma'am.
Yeah.
Yes, I have a question that the cavity which is used as a black body has the and the walls of it has non-zero conductivity. Means why it is that?
Okay. It has to have non-zero conductivity because if it was insulating, then the radiation that is inside it would not affect the wall, and it would just and the radiations would die out. So this emission that we are considering would not happen. So unless the atoms respond to the radiation, you cannot have absorption and emission of the radiation.
Okay. Ma'am, if it is insulated, means how will the energy die out? Means the energy cannot escape that cavity. Means if it is insulated.
Actually, I shouldn't say trap. Actually, the energy would not be generated also, actually, because in the black body you heat it to generate the energy. Yes. So once the radiation, if the radiation would not be emitted only, you would not be able to heat something that is an insulator, right?
Okay.
Yeah, so you need to stop in the first place. Yeah. Good that you asked. I should have clarified that. Okay. I did not spend time on the structure of the black body. I realized later. Fine. Okay. So then the black body radiation, we did the derivations. Now we will come to something else, some other failures of classical mechanics. So these involve the interaction of light with matter. The first effect was the photoelectric effect, which all of you have heard of. Then this was the emission of bound electrons by shining radiation on it, and this could not be explained without quantization. But there are other phenomena that are happening. There is something called Thompson scattering, where light is scattered by a free electron. But this light is simply sort of, you can consider it to be reflected off or absorbed and emitted off, but there is no change in wavelength. There is only a change in direction. This can be explained classically without any problem. A variation of Thompson scattering is the Rayleigh scattering. Here the light is scattered by either you can call it a bound electrons, or you can say it is scattered by the full atom. Here also there is no change in wavelength, it is only a change in direction. These Thompson scattering and Rayleigh scattering, these were classical phenomena. Okay, but then later on, another type of scattering was discovered, the Compton scattering, which was again the scattering of light by free or loosely bound electron. But what was observed was that the wavelength of the light that was scattered shifted. There was a red shift in this wavelength, and the electron was also moved. And this could not be explained without combining both quantum mechanics and relativity. And if you want to describe it even more accurately, then you need quantum electrodynamics. Okay. So we will study the photoelectric effect and the Compton scattering, one after the other. So first, the photoelectric effect. The setup is pretty simple. You have a metal surface and light is shone on this metal surface and it emits electrons. Then there is a detector which is kept at whose potential is variable. So you can either collect all the electrons by making it highly positive, or you can prevent electrons from reaching the detector by making it more and more negative. So this is what was done in each case, that you changed the potential of the detector and you figured out how many electrons reached your detector every second. So this is the quantized by the ammeter. So you just record the current in this circuit. So the more the electrons arriving, the more the current. Okay. Now the two studies were made. So the one study was where the frequency of the light was changed, and the electrons, then the current was measured for various potentials. This was one set of experiments. And the other set was where the intensity of the light was changed and keeping the frequency constant. And again, the current was measured for various potentials of the detector. Okay. Now, the first observation was that no electrons could be detected unless the frequency of the light was beyond a certain threshold. So on the right, if you see the figure, this is a potassium surface. It was found that any photon with below the energy of 2 electron volt could not emit any electron. And after that, the lower the wavelength or higher the frequency of the light that is incident on the metal, the faster the electrons that are emitted. Okay. Now, for the history of the photoelectric effect, you can read this PDF that I have linked to. And the YouTube videos are also nice. They have nice animations. So you can look at them for concept. Now we come to the plots that were obtained. Okay? Like I said, there were two sets of experiments. One was when the intensity was changed, keeping the frequency constant. Here it was found that the negative potential required to prevent any current, this is called the stopping potential. This was the same in all cases. So what does this correspond to? So the more negative the detector, the higher the energy required, a kinetic energy of the electrons required to reach it. So when you keep making the detector more and more negative, first the slow electrons stop reaching, then the faster, and finally the stopping potential would be when even the fastest or the most energetic electrons cannot reach. Okay. So this was called the stopping potential. And this was found to be the same irrespective of the intensity of the light that you shone on it. This itself contradicts classical electromagnetic theory, because there the energy carried by light is proportional to its intensity. So when I am supplying more and more intense light, the electrons should have got enough energy to be emitted. But that was not the case. What you needed was higher and higher frequency. So when you studied the setup with different frequencies of light but same intensity, you found that you got different stopping potentials. And the higher the frequency of incident light, the more negative you needed the detector to be to stop the current, which means that the electrons that were emitted had more and more energy, the higher the frequency of incident light. The other aspect was this constant current that you see on the right when you apply a positive potential. So if you have a positive potential on the detector, you collect more and more electrons because you're accelerating them. And if you have quite a high positive potential, you can be sure that all the electrons are being collected. And this is called the saturation current. The current corresponding to the situation is the saturation current. And with higher intensities, you found that the saturation current was higher. But if you changed frequency, keeping the intensity the same, the saturation current remained the same. Okay? So from this experiment, we got mainly 3 conclusions. One is that there is a threshold frequency below which you cannot emit an electron. By increasing intensity, you somehow increase the number of electrons being emitted. And by increasing frequency, you increase the kinetic energy of the electrons being emitted. And this could be explained again by quantization of energy of the light. Okay, so to do this, the explanation proposed was this: that you assume that these electrons in the metal are bound with some energy E phi. And phi is called the work function. It is in units of potential. And this is the characteristic of the material. So if you do the experiment with different metals, you will get a different threshold frequency. And this is sort of the average binding energy of the electrons in the metal. And you and it was also proposed that the probability of absorbing a photon for these electrons is more or less equal. Now, for one electron to absorb 2 photons and then acquire enough energy to be emitted, this is a possible process, but it is an unlikely process. So we ignore it in the first explanation. Okay. And then we propose that the electrons are ejected if the unit energy of this one photon or one quanta of energy of light is higher than E phi. And whatever the balance energy, that becomes the kinetic energy of the electron. Okay. In addition, the momentum should also be conserved. Yes.
Ma'am, why absorbing 2 photons is unlikely?
Why it is unlikely? Oh, it's just the probability of 2 photons hitting the same electron. That the probability is low. And also, if you look at quantum mechanics, also absorbing 2 photons is also low. The probability of absorbing 2 photons instead of 1. It is just a probabilistic picture that when you're hitting a metal with photons, what is the likelihood that 2 photons will hit the same electron at the same time? Okay, you understand? Yeah, you understand? Okay, I will.
Yes, ma'am.
Yeah, okay. So I will continue. So there is one more thing that needs to be conserved here, that is the momentum. and it is conserved because the lattice recoils, but the energy transmitted to the lattice is considered to be negligible. Okay, if this is not negligible, then what we get is the Compton effect, and that cannot be explained by this simple analysis that we're doing now. For that, we will have to we will study about it. So if the lattice recoils, or if the electron that is scattering the light recoils, then what happens? And when we look at the stopping potential, this can be equated with the kinetic energy of the fastest electron. Fine. Since we don't know the work function of the metal beforehand, what is done is that the stopping potential for various frequencies is plotted, and from this equation, where I've replaced half mv squared with EV0 prime, the stopping potential, then I have this is equal to h nu minus E phi. So EV0 prime is the y-axis, let's say. So y is equal to mx plus c. So the slope will give you h, and the y-intercept will give you E phi. So I can obtain both the wave function and this and Planck's constant from this photoelectric effect experiment. So to do this, we plot EV0 prime for various frequencies, and you get a straight line as you would expect, and the slope gives you h. The x-intercept is the threshold frequency, and the y-intercept gives you the work function. So it is basically quite a simple.
Excuse me, ma'am.
Yeah.
I just want to ask you one thing. Like, we in photoelectric effect, in the from quantum point of aspect, we consider that the collision between the photon and the electron are perfectly elastic. So the photon completely transfers its energy to the electron. So if I cast a light beam on a metal surface with a specific frequency, then all the electrons that are coming out should have a particular kinetic energy, not a variation or a band of kinetic energy.
Okay, so you are confusing theory and experiment in a way. So theoretically, when we write all these equations, we assume that everything is perfectly elastic. Okay, because we want to write the equation. But in reality, not all electrons have the same binding energy. So there is a variation in reality. So when you do the experiment, you get a whole range. In fact, even the stopping potential is not very clean. Okay. So that is why.
You mean that the stopping potential for every electron is not the same?
No, it is not the same actually.
Okay.
But that is why we are considering, see, in the y-axis, it is labeled as maximum photoelectron kinetic energy. So when we use the experimental data to fit our theoretical equation, we only take the electrons with maximum kinetic energy, which have undergone almost elastic collision.
Okay.
Yeah. So and the lower ones, it has somehow the energy has been dissipated, either to the lattice or the binding energy was higher or some problems. That is why we only do the stopping potential and not any potential. If everything was the same, we could have used any potential and seen the current for it.
Okay.
Yeah.
Excuse me, ma'am.
Yeah, this is actual experimental data from Mulliken's original experiment. So if you can take out the data from it, you should be able to obtain the same age as Millikan did.
Excuse me, ma'am.
Yeah.
Ma'am, if you are looking at it theoretically, even in the photoelectric experiment, the variation in energies, even when we talk theoretically, it is like we have the same threshold frequency for the entire metal or the stopping potential, and the variation of energies is because the photon can either hit the electron or not cannot hit the electron. That the variation is because of that, right? Or is it because when we talk about it, it can have different energies as well? I mean, the variation is because there can be a chance of hitting the electron or not, or is it due to there are entirely different binding energies? The energy variation.
The binding energies are different. If the photon does not hit the electron will not be emitted.
Okay.
So the number of photons hitting and the number of electrons being emitted, that is definitely different. The number of electrons are definitely lower. So that is there. But the fact that they have different kinetic energies comes from the fact that their binding energy is different.
Okay, ma'am. Thank you.
So it is the so actually even if the binding energy is actually the same, some electrons are emitted exactly from the surface, some are from below. So even while coming out of this surface, they lose some energy, right? That is also there.
Okay, ma'am. Yes.
Yeah. So if it is not exactly at the surface, while coming out of the surface, it will hit other things in the lattice and lose energy. Okay, fine. So that was about the photoelectric effect. I will ask a question about all these doubts you are having actually in your assignment. So hopefully things will become clearer then. That although it seems like a simple experiment, actually there are many hiccups there. So one of the things is how the stopping potential also does not turn out to be clean when you actually do the experiment, and you have to do many tricks to get a proper value for this. Anyway, you will see that in the assignment. We will now go on to the Compton effect. So in the Compton scattering, what happens is that you have an incident photon, which was taken to be an X-ray by Compton, and he shone this X-ray on an electron at rest, and he observed the wavelength and the direction of the scattered wave, and he found that the wavelength of the scattered X-ray increased, and simultaneously the electron recoiled and shot off in a different direction. So he measured both these angles. So what Compton was lucky in a way, he used a very high energy radiation, and he also used a very small scattering particle. He just took a single electron. So that helped him actually observe this effect. Otherwise, before when people were shining light on metal surfaces and like solid objects, then this recoil was not measurable. So no one can found the Compton scattering really.
Excuse me, ma'am, can you repeat it again? I suddenly got disconnected from the meeting.
Okay, so from Compton scattering, how much have you heard? Have you heard till Compton scattering?
You only said that there is a photon that will hit the electron, and there will be a scattered photon that will that photon will go in another way, and the electron will recoil to the another way.
Yeah, and the scattered photon will have a larger wavelength. And Compton measured both these the wavelength, the energy of the electron, and the two directions in which the electron and the wavelength wave travel. Okay. So there is a detailed discussion in the PDF that I have also uploaded, but I will also do the derivation now. So I will shift to a PDF. I will upload this later, don't worry. So this is now a simplified diagram. So you have an X-ray which has a momentum, the photons have a momentum of P0 and a frequency nu0, and the scattered one has momentum P and frequency nu. This angle is theta, this angle is phi, and the electron is scattered with momentum PE.
Ma'am?
Yeah.
Ma'am, how was this a failure of classical mechanics? Can you...
This was a failure because in classical mechanics, the fact that radiation could deflect matter, this was not possible. So,
okay.
Electromagnetics, the electron could absorb the light and could emit the light, but it could never move.
Okay.
So then,
Excuse me, ma'am. Ma'am, isn't it a postulate, wasn't it a postulate about light itself that if you have an object that some amount will be absorbed, some amount will be transmitted, and some amount will be reflected, and whatever feature that substance is showing, according to that, it will become opaque, transparent, or something like that. So isn't that already a postulate of classical mechanics that radiation can be reflected? We have mirrors for that. Classical mechanics wasn't taking care of mirrors as well or not? I think.
No. So reflection, refraction, transmission, radiation, everything was fine with classical mechanics. But the fact that light could move matter, that was not possible. So the electron could have reflected light, just like in Thompson scattering, as I mentioned. That is fine. But the fact that the electron got scattered itself, and also that the wavelength of the X-ray increased. So the wave lost energy and the electron gained energy. So this was not explainable by classical mechanics.
Okay.
Okay, so it was not that just the scattering part was fine. If the electron stayed in its place and the X-ray just got scattered without changing its wavelength, then this is explainable, and this is called Thompson scattering, as I mentioned. And this would happen, like if you used visible light on an electron, for example, you could very well explain it with classical mechanics, because the recoil of the electron would be very, very small, and you could ignore it. So that's why Compton was lucky. I don't know what he had in mind when he started out with X-rays, but it was because he used a very high energy X-ray that he could observe.
Okay.
Yeah. Okay. And now what happened was, to explain this, we not only need the quantization of energy of the photon, we also needed relativity, but simple relativity, which we shall see. So there are two conservation laws that we will use to find out how much the wavelength of the X-ray is shifted on scattering, on being scattered by the electron. So there is momentum conservation and there is energy conservation. So in the X direction, you have P0 being equal to P cos theta plus P cos phi. This is simple enough. And also in the Y direction, you have the sum being equal to 0. Now here comes the expression for the momentum. So the P0, we express P0 in terms of PE, and we have replaced, wait 1 second. We have converted cos theta to sine theta. Sine phi to sine theta using this expression. Let me just look at it carefully. I shouldn't hurry. So this is this. So we express sine theta in terms of sine phi and sine phi in terms of sine theta. And here we express cos theta in terms of sine theta, and cos phi in terms of sine theta, and cos theta remains the same. Yeah. Okay. Then we have momentum P, which can be expressed as h by lambda. That is the quantization of momentum, and we replace the momentum here. Of the X-rays, we can replace by h nu by c. In addition, we have the energy conservation. Okay, so the X-ray plus electron at rest should be equal to energy of scattered X-ray plus scattered electron. And here we need to use the relativistic expression for energy of the electron. Okay, so this is the rest. No, not really. So this is the rest energy plus the momentum related energy. And we have then from the energy conservation, this is h nu 0. Electron at rest is only the rest energy. The scattered energy is h nu, and the scattered electron has energy EE, which is given by this expression. Okay. Then we manipulate this From the momentum expression, we manipulate this to get this difference between the original X-ray and the scattered X-ray, and then we do some algebra and finally get the shift in the energy of the X-ray in terms of the energy of the electron. Okay. Then we manipulate this further to eliminate EE, and we only want to have an expression for nu minus nu zero. Okay. And you can go through this carefully later. We are running out of time. But it's simple algebra, and then you get this expression. Okay. So nu is the frequency of the scattered X-ray, and nu zero is the original X-ray. And the interesting thing to note is that it only depends on theta. It does not depend on phi, and it also does not depend on the energy of the scattered electron. Okay. So you can read about the implications of this a bit more in the PDF that I provided. So there they discuss the implications of the expression a bit more, and I'm sure you can easily convert this to lambda. There is no confusion here. Here you can simply replace nu by c by lambda, and you will get an expression. Now, something that you encounter very often when you read anything about Compton scattering is the Compton wavelength. So I will just define it for you. It is the wavelength of a particle. The Compton wavelength of a particle is equal to the wavelength of a photon whose energy is same as the rest mass energy of that particle. Okay? So it is just a quantity, a theoretical quantity. So the Compton wavelength, it does not manifest itself. It's just a unit conversion from rest energy to a wavelength, which helps us to compare quantities. And you can also express the frequency shift of the scattered X-ray in terms of the Compton wavelength. Okay? And the Compton wavelength, as you can see, it is normally a very, very small quantity. Because H is very small and C is large. So unless, yeah.
What's the utility of this quantity of the quantum wavelength of a particle?
So basically, sometimes you express the shift in the scattered wave of the wavelength of the scattered X-ray in as fractions of this Compton wavelength, and you do some analysis that if the wavelength of incident radiation is a certain percentage of the Compton wavelength, then the scattering is a certain percentage of the Compton wavelength. Because you encountered it often, I define it. You will not really need it in the course.
Okay.
And the last thing in the last 5 minutes, because this is something you all know, I'm sure, it is the hydrogen atomic spectra. So this was one of the first quantum phenomena that was observed. Like the quantization of the energy levels of the atoms was clear from the very beginning once the hydrogen atomic spectra was measured. But to explain it completely, it took a very, very long time. So you needed both the quantization of atomic energy levels, and you also needed the quantization of light to explain this spectrum. And eventually, when both were established after the photoelectric effect and the black body radiation, these two were accepted. Then Bohr combined the two quantizations to explain the hydrogen atomic spectrum. So he could explain the basic structure of this spectrum, but there were still finer aspects which required more development of quantum theory. And I will not discuss this in great detail now, because you will do a full solution of the hydrogen atom, a quantum mechanical solution, and then the spectra will come back and you will know the explanation for the fine structure as well. But Bohr could explain the Redberg formula. So Redberg had sort of found a formula which fit the series of lines. So you see the formula here, which is 1 by the wavelength, is a constant, which is the Redberg constant for hydrogen. And you have two integers here, which is that one was the final energy level, so the level from which the transition is occurring. And this is the initial or the lower energy level to which the electron is falling. Okay, so if you use the terminology of emission spectrum, and if you talk about absorption, then this is really the Ni is really the initial energy level, and Nf is the final energy level. And the same formula could be applied to hydrogen-like atoms. So atoms with one electron but higher nuclear charge. So let's say helium plus, lithium 2 plus, beryllium 3 plus, etc. And then you have this factor Z square, where Z is the atomic number. Okay. This Redberg constant RH was obtained to be this value from experiment. And one can get the Redberg constant for any atom from this relation, where R infinity is the Redberg constant assuming infinite nuclear mass, and this is the reduced mass of the electron in that atom. R infinity is basically a theoretical quantity, so which has this value. And from this you can compute the Redberg constant for any material, and then this expression will give you the lines of the atomic spectrum. And as I said, there is also the fine structure of lines which require a full quantum treatment. These only give you the basic peaks, but some of these peaks are actually 2 peaks if you go in for a higher resolution, 2 or more peaks. And the important thing to note is that this formula, it works well only for 1 electron atoms, because here the structure of the electrons is not considered. It is only a single electron which is considered to be jumping about under the influence of the nuclear charge. So that is all I will say about the hydrogen atomic spectra now. And once you do this full solution, we will come back to it and look at how the lines can be explained. Okay. I will stop here because it's almost time, and we have been advised to leave you at least 5 minutes before. So if anyone has any questions from today, like some immediate questions, you can ask me now. No questions? Okay, then I just wanted to tell you one more thing. So we have been asked to upload the videos to YouTube as a channel. So some people are having difficulty looking at the videos from Google Drive, but I have not managed to do this yet. But once I do it, I will let you know. And the YouTube link will also be on the WeLearn page. So I just wanted to, if someone can actually help me. I was trying today to upload it, but there is no way to directly upload from Drive to YouTube. So if any of you are, some YouTuber and you know how to do this, just drop me a line and then I can talk to you about how to do it. Okay. So I will stop presenting now and go back. Okay. So bye-bye. I will.
Ma'am?
Okay. So a lot of you had problems, it seems. Yeah. Someone said ma'am.
Ma'am, any suggestive books for reading these?
No, actually, I am avoiding even looking at any book because I know you all have problems accessing books. So it's better to just rely on the online resources that I provide. Okay. If you have a book, you can read it if you like. It will clear concepts, but otherwise it's fine.
So for clearing concepts, any book you prefer? Means
if you have Atkins, that is a book I like.
Atkins Quantum Mechanics.
Atkins Quantum Mechanics, yes. And other than that, you can actually, this is like very basic quantum mechanics. So any book is actually fine.
Okay.
Yeah. But what I try to do is I'm trying to link it to the latest things. So that part you will have to rely on me. But I will not ask questions from it.
Okay.
Yeah.
Thank you.
Don't worry.
Hmm.
Yeah. Okay. Thank you. Bye bye.